Hello, everyone. I'm Abhijit, and I'll be talking to you all about our paper, Time-Space Lower Bounds for Simulating Proof Systems with Quantum and Randomized Verifiers. And this is joint work with Ryan Williams at MIT. So for starters, this is a pretty long title, so let's break it down a bit. So what are time-space lower bounds? Well, let X be either a specific problem or a set of problems, so a complexity class. Excuse me. Our goal is to show that X cannot be solved by algorithms that are simultaneously fast and use a limited amount of memory. So there could be a fast algorithm or there could be a small space algorithm, but we want to show that there's no algorithm that's both at once. And when X is a complexity class, by the way, we just mean that there is a problem in X that does not have such algorithms. And it'll be helpful in our data results to define the following complexity class. So let TS n to the C be the class corresponding to random access machines that are simultaneously n to the little o of one space and O of n to the C time. And with this in mind, we can give our first example of a time-space lower bound, which is due to Ryan Williams in 2007. And it's that SAT, the satisfiability problem, is not contained in TS n to the C if C is less than 1.801. So what is this saying? This is just saying that there is no random access machine, which runs in, say, log n space and n to the 1.8 time, that solves satisfiability on length n inputs. And the reason I wanted to bring this theorem up now is because all our results are going to be more or less of this form. They're going to be of the form a problem in X, where X is some complexity class, cannot be solved by a Y machine. Y is going to specify the computational model that uses small space and O of n to the C time if C is smaller than Z. Z is going to be some constant like 1.801. Cool. The other part of the title was proof systems with quantum and randomized verifiers. So what are those? Well, they're complexity classes. You're all probably familiar with NP, which is those languages whose yes instances have classical proofs, which can be verified in polynomial time by a deterministic verifier. And by classical proof here, I just mean like a bit string. So we have a prover, and the prover sends a proof to the deterministic verifier, and the verifier processes the input and the proof together and returns 0 or 1. And so you should think of this in our language as a proof system with a deterministic verifier. So now, what might a proof system with a randomized verifier be? Well, it means that we allow the verifier to use randomness. And this gives us the complexity class MA, or Merlin-Arthur. We can go one step further and allow the verifier to be a quantum algorithm, in which case we get Qcma. Qcma is quantum classical Merlin-Arthur. Note here that the proof itself is still a class. It's still classical. There's no quantum element to the proof, but the verification procedure is quantum. And Qcma is an example of a proof system with a quantum verifier. And it's actually the complexity class we're going to focus on in this talk. Some of you might have heard of Qma, which is similar to Qcma, but the proofs are also allowed to be quantum. We're not really going to talk about Qma in this talk, but I just wanted to mention it to make the distinction clear. So with all this in mind, we can now state the results. Actually, one more thing I should say before I state the results is that QRAM is going to stand for a quantum random access machine. And if you aren't familiar with quantum random access, then think of it analogous to classical random access. There is some standard model of quantum computation. In our case, we're going to take the uniform quantum circuit model. And quantum random access is essentially a way to it essentially gives the machine additional power to access certain parts of the data, workspace, input, etc. And if you want more details on this, you can check out our paper. But our theorems are pretty robust to most standard notions of QRAM. Cool. So theorem 1 is that linear time QCMA on a QRAM, or QCMA time n, as we'll call it henceforth, is not in TS n to the C for C less than 2.366. So what does linear time QCMA on a QRAM mean? Well, it means that the verifier is a quantum random access machine, and it runs in time linear in the length of the input. So it receives like it has an input, and it receives something from the it receives a proof string, and then it runs some linear time verification process on a QRAM and uses that to decide whether to accept or to reject. And you should compare this to the classical analog of this theorem, which is due to Williams from 07. And it's that non-deterministic linear time on a RAM or n time event is not in TS n to the C for C less than 1.801. So the sort of how you should think about these two in relation to each other is that n time n is contained in Qcma time n. And so essentially we're saying, okay, if we make the complexity class in question bigger from like n time n to Qcma time n, or bigger probably, then if we make the complexity class in question bigger, we can prove a stronger lower bound because we're able to increase the lower bound exponent from 1.801 to 2.366. Cool. So, and both theorems are obtained via the method of quantifier trading proofs. And we're going to talk a lot about quantifier trading proofs during this talk. But briefly, before I get to the sketch of theorem, before I get to like the methods and techniques used to prove theorem 1, I just want to briefly mention the other two theorems in the paper. We're not going to talk very much about those, but I just wanted to state them just so they're in your minds. Theorem 2 is that there exists a problem in linear time MA on a RAM, which is not decidable by bounded error probabilistic RAMs using O of log n space and O of n to the C time for C less than 1.465. So there's a couple of things to unpack here. First off, linear time MA on a RAM, this is defined in the same way as linear time QCMA on a QRAM is. The verifier is a random access machine, and it runs in, it's a random access machine that's allowed to use randomness, hence Merlin Arthur, and it runs in linear time. But the other thing is that unlike before, where we're sort of unlike before where we were talking about TS n to the C, here the RAMs in question are probabilistic because it's not decidable by bounded error probabilistic RAMs, and so the flavor of the proof is a little bit different, but the essential ideas are pretty similar. And this is an improvement over a result of Deal from 07, who proved theorem 2 for C less than 1.414 square root 2. Theorem 3 is that if we replace linear time MA on a RAM with linear time QCMA on a QRAM, we can increase the lower bound exponent to just under 1.5. Cool. I'm not going to talk about theorem 2 and theorem 3 for the rest of the talk, but you're welcome to check out the paper for details on this. So here's a roadmap for the rest of the talk. We're first going to talk about how we can get time-space lower bounds from quantifier trading proofs. And in particular, we're going to talk about speed up and slowdown rules, which are the key components of a quantifier trading proof. We're then going to talk about how we can get quantifier trading proofs with generic slowdown rules, or in particular, how we can get sort of better quantifier trading proofs with generic slowdown rules. And the generic slowdown rule methodology is something we introduced in this work. And third, we're going to talk about how we can get generic slowdown rules in the quantum setting from using Gerber's algorithm. And sort of the idea is Gerber's algorithm gives us a generic slowdown rule. Generic slowdown rules give us better quantifier trading proofs, and better quantifier trading proofs mean better lower bounds. And that's how this entire thing is going to fit together. And just henceforth, in the rest of this talk, I'm going to play fast and loose with small terms, meaning constants and subpolynomial factors. I'm just going to hand wave away. And if you want those details, you should check out our paper. Let's start off by talking about quantifier trading proofs. This is mostly going to be a review of existing work. So like for the most part, this isn't going to be anything that we did in this work, but it's worth giving that background now. So the key components of quantifier trading proofs are alternating complexity classes, which are, or you should think of these as fine-grained versions of sigma kp or pi kp for some positive k. So like, and the sigma kp and pi kp are the levels of the polynomial hierarchy. And what do we mean when we say fine-grained? Well, an example is something like this. Exists n squared for all n to the 0.3, ts n to the fifth. So this is something in sigma 2p. But we want a little bit more, we want to be precise about how exactly this works. And so let's give an example of a machine in the class exists n squared for all n to the 0.3, ts n to the fifth. So on an n-bit input, there's going to be 3 stages of computation. The first is that we're going to guess a length n squared string, and then feed the input and our guessed n squared bit string into an intermediate small space machine. The output of the intermediate machine is then going to go to another intermediate machine along with the guess from the second quantifier. And the output of the second quantifier has to be of length n to the 0.3. So like the exponents are telling us how large the guesses are essentially. And then the output of the second intermediate machine goes to an n to the 5th time small space machine, hence TS n to the 5th. And this is going to return 0 or 1. And as a standard for classes in the polynomial hierarchy, we accept if and only if there exists a guess from the first quantifier, such that for all guesses from the second quantifier, the verifier accepts. I am being hand wavy here. There's important details with like how exactly the intermediate space machines work that do matter and that I'm glossing over for the purposes of this talk. But you should, if you're curious about this, you should definitely check out the paper since we elaborate on this a lot in the preliminary section. I think the one thing that's worth stating though is that like this, for the purpose of this talk, you can pretend that the runtime of the intermediate space machine is smaller than the runtime of the last machine. So like basically the intermediate machines are fast enough. They're not really going to affect the runtime. You shouldn't really worry about them. I guess also one other thing I should say is that I'm going to be pretty sloppy with like big O notation henceforth. So like I might say like, if I say n squared, I might actually mean O of n squared, or if the notation says n to the 5th, it might actually mean O of n to the 5th. This shouldn't be too important in order to follow the basic logic. But yeah, just to keep our wordage clear, I'm going to call the existential quantifier and the subsequent intermediate machine the existential part, the universal quantifier and the subsequent intermediate machine the universal part, and the last machine the verifier. Oh, and in case you're curious, this photo is one of Soren Kierkegaard, a famous existentialist philosopher. Cool. So with this in mind, we can say a little bit more about quantifier trading proofs. So as mentioned, they're built up from alternating complexity classes, which are fine-grained versions of sigma kp or pi kp. And we gave an example of a machine in such an alternating complexity class. And now a quantifier trading proof is just a conditional sequence of inclusions of alternating complexity classes. And how do we show inclusions? Well, there's two ways, the speedup rule and the slowdown rule. Let's start with the speedup rule. The speedup rule adds two quantifiers to an alternating complexity class and reduces the runtime of the verifier. And for example, we can use the speedup rule to show that TSN squared is contained in exists n for all log n TSN. And this is just saying that every language that's decidable by a machine in TSN squared is also decidable by some machine in exists n for all log n TSN. The idea is that we can break the computation of any TSN squared machine into n pieces, each of which will be n steps long, and verify each piece separately. So if, say, this is the computational tableau of a TSN squared machine, note, by the way, that it's n to the little o1 space because TS is a complexity class of corresponding to small space machines. So now on an n-bit input from a language in TSN squared, so an accepted input, the existential part guesses n plus 1 configurations, each of which has size n to the little of 1. And the configuration this guesses will be the initial configuration, n minus 1 intermediate configurations, and the accepting configuration. So these are the guesses of the existential part. Then the universal part picks a pair of adjacent guessed configurations and discards the other states. And note that this only takes roughly log n bits because there's n plus 1 configurations and you just want adjacent pairs. So it'll be something like this. And then the verifier runs for n steps, starting at the first configuration it receives and accepts if it reaches the second. And the idea is that since the existential part can guess the actual intermediate configurations of the original TSN squared machine, we'll accept if the input was in the language. And you can work out what happens if the input is not in the language. Two important things to keep note of here are that first, that the speedup rule produces small quantifiers, as in over log n bits. The second is that the universal part in the machine on the right-hand side of the inclusion is essentially acting as a search for a bad intermediate configuration. And this is going to be important later. So a slowdown rule removes a quantifier from an alternating complexity class at the cost of increasing the runtime of the verifier slightly. And slowdown rules are generally going to be conditional on some assumption. So for example, assume that n time of n, non-deterministic linear time on a RAM, is contained in TS n to the c for some c greater than 1. Then exists n for all n TSN is contained in exists n TS n to the c. And to see why this is the case, notice that on the left-hand side of the inclusions, the universal part and the verifier together, so that's for all n TSN, this together is something from cohen time n. And Well, note that the assumption n time n in Tsn to the c also implies that co-n time n is contained in Tsn to the c, because Tsn to the c is closed under complementation. And so then the inclusion follows. Cool. So with this in mind, we can now fully describe quantified trading proofs. So as mentioned, alternating complexity classes are fine-grained versions of levels of the polynomial hierarchy, and we give an example of a machine in an alternating complexity class. And quantified trading proofs are conditional sequences of inclusions of alternating complexity classes. And we have two ways of showing such inclusions: speedup rules, which add quantifiers and reduce their runtime, and we give an example of such, and a slowdown rule, which conditionally removes quantifiers and increases the runtime, and we give an example of a slowdown rule as well. The idea is that given stronger assumptions in the slowdown rule, we can prove stronger inclusions. And ultimately, we can even prove impossible inclusions. We can prove inclusions that violate some sort of a time hierarchy theorem. And this, if we're able to do so, this means that the assumption we use must have been false. And in particular, the contradiction we're going to go for is that Tsn to the d is contained in Tsn to the d prime for d prime less than d. This isn't on its own a contradiction because we don't have a Ts hierarchy, but it turns out that this implies a contradiction in our setting. So here's an example of a time space, of a quantified trading proof dating back to Lipton and Viglas from '99. So let's start by assuming that n time of n is contained in Tsn to the c for some c greater than 1. Let's start with Tsn squared. So basically, Tsn squared is going to be the first alternating complexity class in our chain of inclusions of alternating complexity classes. So you can visualize the computation as follows. You have an n-bit input. It goes into an n squared times small space machine, which then outputs 0 or 1. We can start by applying the speedup rule, which shows that Tsn squared is contained in exists n for all log n Tsn. We mentioned how this might be proved earlier. And this is now what the right-hand side looks like. We have an n-bit input, the existential part, the universal part, the verifier, and the output. By the definition of co-n time n, this the universal part and the verifier together are just a co-n time n machine. And so by assumption, as mentioned, we can replace this with Tsn to the c. This can be thought of as an application of the slowdown rule. Now, this in turn is now in n time n to the c. Why is that? Well, we can squash the intermediate machine and the n to the c time machine into a single n to the c time machine. Again, we're assuming that the intermediate machine is not contributing too much to the runtime. This ends up being true. And so after the squashing, this is what the computation looks like. And now it's clear that we have an exists n part, which is the proof essentially, and the verification is n to the c time. So overall, this is an n time of n to the c. By assumption, if we we can use a slowdown rule, which can be thought of like assumption plus a padding step to show that this is an Tsn to the c squared. Because if n time n is in Tsn to the c, then n time n to the c is in Tsn to the c squared. And now we have a contradiction if c squared is less than 2. And that statement holds regardless of whether you read the exclamation point as a factorial or as punctuation. So now we see that n time n is not in Tsn to the c for c less than the square root of 2, because if c less than square root of 2, then c squared is smaller than 2. This is nice. How do we do better? Well, this was achieved by Ryan Williams. This was achieved in several works building up to Ryan Williams' time space lower bound for n time n from 07, which is that n time of n is not contained in Tsn to the c for c less than 1.801. And the proof is somewhat similar with one major difference. Assume that n time of n is contained in Tsn to the c for some c. This gives us a slowdown rule. And now we may apply the speedup rule and this slowdown rule in a carefully chosen order. This is the really important part. Essentially, the content of quantified trading proofs is coming up with the right order and the right set of parameters in order to prove the strongest inclusions possible. And I won't go into how one comes up with these things, but you should check out this paper, the paper of Williams 07, if you are curious about how these were initially proved. But ultimately, we can show that Tsn to the d is contained in Tsn to the d prime for d prime less than d if c is smaller than 1.801. So because n time n is contained in Qcma time n, we automatically have that Qcma time n is not contained in Ts n to the 1.8 because n time n is not contained in Ts n to the 1.8. So Qcma time definitely shouldn't be. So let's consider c greater than 1.8. And we want to show that even this cannot work for at least some c that are larger than 1.8. So yeah, now we're getting to the new contribution of this paper, which is getting better bounds for linear time Qcma. So let's introduce the notion of a generic slowdown rule. A generic slowdown rule is a slowdown rule. So again, slowdown rules are conditional quantifier removing rules, basically. And a generic slowdown rule is a slowdown rule associated with some parameter between 0 and 1. It's allowed to be 1. It's not allowed to be 0. And conditionally shows inclusions of the form. It might show something like exists n for all log exists n squared for all n. Ts n to the 5th is contained in exists n squared Ts n to the 5 alpha c. And just to be clear, the regular slowdown rule is generic with alpha equals 1. So the slowdown rule we've been discussing so far, before this slide, it would have shown exists n squared for all n Ts n to the 5th is contained in exists n squared Ts n to the 5c. This is the same sort of padding argument that we used a few slides ago. But the key idea is that if we can prove a generic slowdown rule with an alpha that's less than 1, then we get a stronger inclusion. And stronger inclusions mean stronger lower bounds and contradictions for larger values of c. So that's basically how we're going to proceed. We're going to try to prove a generic we're going to try to show that some assumptions that we're able to make imply generic slowdown rules for an alpha that's smaller than 1. So what exactly does this give us first? Well, we can do some algebra and we get the following theorem. Let x be complexity class. And here's the theorem. If the assumption x is contained in Ts n to the c implies a generic slowdown rule with parameter alpha, then x is not contained in Ts n to the c whenever x is smaller than the largest root of some polynomial that depends on alpha. So here's an example. Assume that n time n is contained in Ts n to the c. This implies a generic slowdown rule with alpha equals 1. It turns out to, rather. So plugging alpha equals 1 into this theorem, we get the polynomial x cubed minus x squared minus 2x plus 1. The largest root of this polynomial is 2 cosine pi over 7, which is roughly 1.801. And this is actually an alternate proof of the earlier result that we mentioned, which is that n time of n is not contained in Ts n to the 1.801. So we already see how this gives us an existing theorem. Now, how do we use it to get something new? Well, we want to apply the theorem when x is Qcma time n, which again is linear time Qcma on a QRAM. And the way we're going to do this is that we're going to hope that we can get a generic slowdown rule with a smaller value of alpha from the stronger assumption, because the assumption Qcma time n is contained in Ts n to the c for a given c is stronger than the assumption n time n is contained in Ts n to the c. And we're hoping that the stronger assumption means a smaller alpha and hence a stronger lower bound at the end. Cool. So now we're on to the next step, which is how do we prove generic slowdown rules in the quantum setting? Spoiler alert, it's going to be with Gerber's algorithm. So think back to when we were discussing the speedup rule, and we mentioned these two important points. The first was that the speedup rule produces small quantifiers, and by small I mean like log n, things like log n, as opposed to things like n squared or n. And the second is that the universal part is essentially acting as a search for a bad intermediate state. It's essentially because the existential part is guessing intermediate states, and then the universal part is checking to see if there's a adjacent pair of bad intermediate states, which is inconsistent, where like I can't run computation from one state and reach the other in the specified amount of time. So we're going to essentially use a quantum computer to efficiently remove small quantifiers. And well, in this case, the small quantifier is acting as a search. So the idea is that we can use Gerber search. So in case you're not familiar with Gerber's algorithm, here's a quick overview. Gerber's algorithm is designed to solve the following problem. Given f from 0, 1 to the m to 0, 1, find x such that f of x equals 1. So essentially, we're inverting f at the output 1. A deterministic machine may need 2 to the m evaluations of f in order to solve this problem, because it just needs to try every single input and hope that it hits 1 sooner rather than later. A quantum computer can do better. A quantum computer can actually solve this theorem using O of 2 to the m over 2 evaluations of f. So this is like roughly a square root improvement over the deterministic machine. And now let's try applying Gerber's algorithm to exists n for all log n tsn. So as mentioned, a machine from this complexity class takes an n-bit input. There's an existential part, a universal part, a verifier, and the output. So let's start by sort of combining the second intermediate machine and the verifier. And then let's fix the output from the existential part. So now what we're left with is the green box, which is a function of the guess of the universal quantifier. So it takes the guess from the universal quantifier along with the fixed output of the existential part and returns 0 or 1. We're going to apply Gerber's algorithm to the green box. So just to make it clear, like the reason this makes sense the reason we want to do this is because the universal quantifier is basically saying, or rather the way this machine is being used is that we're asking, is it true that for all log n bit strings, the output of the green box is 1? Because if so, then we're happy, and if so, then we accept essentially, and if not, we reject. So essentially what we're doing is a search. So we just want to search over all the possible inputs and see if there is an input that all the possible inputs, as in all the possible guesses from the universal quantifier, and see, is there a guess that gives us 0? Well, we can invert the green box with root n evaluations of the green box, because 2 to the log n over 2 is root n. Each iteration of the green box takes O of n time. Again, we're assuming that the intermediate space machine doesn't really matter asymptotically. So that means that we can replace the universal part and the verifier. So like this and everything that's on the screen right now, everything in the diagram can be replaced with an O of n to the 3/2 time quantum machine. So now putting back the existential part, we see that we have an input, the existential part. We have the input, the existential part, and the n to the 3/2 time quantum machine. This machine is in Qcma time n to the 3/2 by padding, or really by definition. And if we assume that Qcma time n is contained in Ts n to the c for some c, then now by padding, we can replace the quantifier and the quantum verifier with Ts n to the 3c over 2, because Qcma time n to the 3/2, and then we multiply it by c because Qcma time n is contained in Ts n to the c. So this is what we're left with in the end. An n-bit input goes into a deterministic n to the 3c over 2 time small space machine. But remember that earlier when we did the same thing with the Lipton-Viglas argument, we got n to the c squared. So like essentially we've done better than what we sort of got with the original argument when c is greater than 1.8, or really when c is greater than 1.8, this is an improvement. And this is sort of the key idea. Like by using Gerber's algorithm rather than by just using the slowdown rule, we're able to show stronger inclusions than we are otherwise. So now we can just do some technical stuff and ultimately obtain the following. Lemma: the assumption Qcma time n in Ts n to the c yields a generic slowdown rule with parameter alpha equals 2/3. Just to recap how this sort of happened, we saw in the example that we're able to do better than the Lipton-Viglas bound by using Gerber's algorithm to remove a quantifier rather than just using the slowdown rule via assumption. And it turns out that when one works this out, you can show that it actually it yields a generic slowdown rule of parameter alpha equals 2/3. We earlier showed that if the assumption x in TSN to the C implies a generic slowdown rule with some parameter alpha, then x is not in TSN to the C if C is smaller than the largest root of some polynomial dependent on alpha. So now that we have a value of alpha and a generic slowdown rule, we can plug alpha equals 2/3 into the theorem to get Qcma time n is not contained in TSN to the C for C less than 3 plus square root of 3 over 2, which is roughly 2.366. And there we have it. This is theorem 1 as promised. So now let me just briefly close by talking about some future work. One thing that would be really nice is that we'd like to get a lower bound on a specific problem. Like we have a lower bound on Qcma time n. So that means there's some problem in Qcma time n that can't be solved by small space fast algorithms. But we'd like ideally a lower bound on a specific problem. Like we'd like to ideally be able to say like, oh, this problem, this is the hard one here. And a candidate problem is the k-local Hamiltonians problem, since it's a QMA complete, so it's definitely hard for Qcma. And recall this theorem from earlier. We didn't show this, but we mentioned that SAT cannot be solved by a RAM that uses small space and O of n to the C times simultaneously if C is less than 1.801. The idea of this proof is that we can pass from the n time of n lower bound, which we also mentioned earlier, to the SAT lower bound. And by this, like earlier, we showed that n time of n is not contained in TSN to the C for C less than 1.801. And the idea is that it turns out we can pass from that lower bound on a complexity class to the specific lower bound on SAT. And we sort of hope to do the same for our lower bound on Qcma time n. And how does it work in the classical case? Well, first, one shows that non-deterministic linear time on a RAM is not contained in TSN to the C for C less than 1.801. This is n time n is not contained in TSN to the C for C less than 1.801. There's a theorem of Gurwitch and Shala from '89 that shows that non-deterministic linear time on a RAM is quasi-linearly, so up to polylogs, equivalent to linear time NP on a multi-tape Turing machine. So we've gone from RAMs to multi-tape Turing machines. That's what happened here. This should say non-deterministic linear time on a RAM is quasi-linearly equivalent to non-deterministic linear time on a multi-tape Turing machine. And it's a theorem of Cook from '88 that SAT, the satisfiability problem, is complete for a non-deterministic linear time on a multi-tape Turing machine under quasi-linear size, quasi-linear time, small space reductions. So putting all these together gives us, lets us pass from lower bound on n time of n, non-deterministic linear time on a RAM, to SAT, because essentially it says, okay, well, a lower bound on non-deterministic linear time on a RAM is equivalent to a lower bound up to polylogs equivalent to a lower bound on non-deterministic linear time on a multi-tape Turing machine. And SAT is complete for non-deterministic linear time on a multi-tape Turing machine. So chaining these together, we get that SAT also cannot be in TSN to the C for C smaller than 1.801. So now, how do we lift this to our setting? Well, the theorem that we proved in this talk is that linear time Qcma on a QRAM is not contained in TSN to the C for C less than 2.366. We also know that 2 local Hamiltonians is hard for linear time Qcma in the uniform circuit model under quasi-linear size, quasi-linear time, small space reductions. But what's missing is this middle link. We'd like to show, ideally, that linear time Qcma in a QRAM is quasi-linearly equivalent to linear time Qcma in the uniform circuit model. And if we can show this, then we have a lower bound on 2 local Hamiltonians, which would be nice. But that's essentially the abstraction right now. Cool. That's all I really wanted to talk about today. So thank you for your time, and I hope you all have a wonderful day. Thank you.